Alrighty, welcome back to operating systems. So we got introduced to page tables. Any questions about the last lecture? All right, so we had page tables. We use that to translate blocks of memory at a time. We're just going to riff on that, but we're going to fix our major issue. So our major issue before was that the page table size was humongous. So remember what we had before. We had our virtual address, and we said we will only go ahead and translate 39 bits. So we took that VPN, so we took that whole 39-bit address, separated it out into two parts. We made blocks, so our page size was 4 kilobytes, or 2 to the 12. So we had 12 bits here for an offset, and then 27 bits here to basically select which virtual page we were talking about. And then we use that as an index into this page table. And how many entries were in this page table? 2 to the 27, right? So we had 2 to the 27 entries. And then it's basically like a big old array. So each entry was a page table entry, right? That had a valid bit that stored the PPN and some other bits of information, but the valid bit in the PPN was the most important thing. And the size of the page table entry for this one was 8 bytes. And through this page table entry, right, that's how we got our PPN, which was 44 bits just because. And then the offset remained the same. It was still the 12 bits. So when we translated, the offset stayed the same. That's just which byte on the page do we want to access. And then we use the page table to get us from a virtual page number to a physical page number. So each of these entries were 2 to 3 bytes. So how many bytes is that big old page table? Yeah. 1 gigabyte, or depends how you want to write it. So if there are 2 to the 27 entries, and each entry is 2 to the 3 bytes, well, the total size of that is 2 to the 27 times 2 to the 3, which due to exponent law is the same as 27 plus 3, or 2 to the 30, and then, right, 2 to the 10, that is equal to 1 kilobyte. 2 to the 20 is 1 megabyte, and then 2 to the 30 is 1 gigabyte. So remember, each process on your machine has its own page table because it has its own virtual address space, so it needs its own page table. So let's say I was running 16 processes on my machine. How much memory is used for page tables? 16 gigabytes. If I have only 16 gigabytes of RAM, how much RAM is left over for my programs to use? 0. Would anyone enjoy using an operating system that worked like that? That all your RAM just goes to page tables, which you didn't even know existed before this course? Probably not. So let's fix the issue. So what's the easiest way to fix this issue? Page table's too big. What's the easiest fix? Make it smaller, right? So if I want to make it smaller, well, that means I can only translate fewer virtual addresses, so we'll have to do something about that. But we'll have some insight here where, hey, we already took our memory, so say this was all of memory. and we just divided it up into fixed size blocks that we called pages. So all of memory looks something like this. And then, right, if we weren't doing anything clever, our page tables also need to live somewhere inside of physical memory. So we didn't argue about what would happen to them before. So if my page table, maybe my big page table, maybe that exists in like all this physical memory, I'd have to keep track of, where it starts, how big it is, maybe how many blocks it contains. It's a whole mess. It's easier if I just use blocks to store page tables and just use blocks of memory at a time, and then my memory allocator, all it has to deal with is blocks. So each of these blocks, right, they're 2 to the 20 or 2 to the 12 bytes. So one thing I can do to make my page table smaller and make my whole system overall easier is I can have a smaller page table, and I can make the table small enough that it fits on an individual page in physical memory. So if I made my page table fit in physical memory, how many entries could I have? So my total size, so if my page size is 2 to the 12 and my page table entry size is 2 to the 3, or aka 8 bytes, then how many page table entries could I store on a page of memory? Uh-oh. 2 to the 9, right? So this is my size. Each entry is this, so it's just division. Nothing tricky yet. So it's 2 to the 12 divided by 2 to the 3, which due to exponent law, 2 to the 12 minus 3, or 2 to the 9, right? So if I made my page table fit exactly on a page, then I could fit 2 to the 9 entries. So if I do that, I would have a system that looks like this. So I take my virtual address, and instead of all the 27 bits that I had before, to make my page table fit exactly on a page, I would need 2 to the 9 entries. And then as part of translation, your MMU, or memory management unit, is going to know which page table to use for the translation. So using that and then getting the index from the bits, that will tell you which page table entry you should select, and then that page table entry will have the PPN, and we could go ahead and translate the address. So this is the same as before, but now our page table actually fits on a page. So is everyone okay with that? So obvious drawback here is that our whole virtual address in this case is now 12 plus 9. So I can only use 2 to the 21 bytes of memory in my program now, which is what, like 2 megabytes, which is a pretty lame program that only uses 2 megabytes. So first off, before I show you what we really do, any questions about this? Okay, it's going to get weird. All right, here is what actually happens. This is what how virtual memory translation actually happens on your machine. So it uses that idea where we have a page table that fits on a page, but in order to actually translate all of the addresses we could before, we can use multiple levels of page tables so that eventually we can actually translate the same number of addresses in total. So how this works is it takes that 27-bit VPN and then splits it up into multiple levels. And then because, well, if we take 27 divided by 9, it means we need 3 different levels of page tables. And how that works is this register, which tells you which page table to use to start your translation. That still exists, but now the difference is from the virtual address, we take these 9 bits, and then it tells us which entry to actually access into this page table. So this one will fit in a page. That's why it's 9 bits. So this will tell us the index to use in the L2 page table, and then we take some additional steps. So in the L2 page table, the page table entry there, the physical page number there, it tells us where to go find the next L2 page table. Then at the L2 page table, from the virtual address, we figure out what index we need to look at to get an entry. Then we find the entry. The entry will have a physical page number, and instead of telling us which page this virtual address should translate to, it tells us what L0 page table to use. And then we have the next bits here that tells us the index we used for this table. And then finally, mercifully, the PPN that we get in the L0 page table, that's the PPN we use for a translation to actually get the physical address. Whew. So why would this be a lot better? Doesn't this look like a whole hell of a lot of work? So, main question, looking at that, how much space do I need to consume to translate a single virtual address? Yeah. So in this scheme here where I have 3 levels of page tables, how much memory do I need for page tables to translate a single virtual address? Because before, when we had that single giant page table, we needed a whole gigabyte even to translate a single address for a program. Yeah. 512 bytes? How do you get that? Don't know, that's okay. Yeah?
Is this 6 megabytes?
6 megabytes. How did you get 6 megabytes?
It's like each page table is using 2 megabytes, and then there's 3 page tables.
So each page table is using 2 megabytes. So not quite, but you're on the right track. So each page table looks like this from before, where it takes up a page, right? Which is 4 kilobytes, not 2 megabytes. Yeah, so it would be 12 in order to translate a single address. So in order to translate a single address, I need 12. So I need one L2 page table, one L1 page table, and one L0 page table. Yeah. So how do I know each page is using 4 kilobytes? So we have 9 bits here for the index into it, and same reason why we pick this size. So there's 2 to the 9 entries, and then each entry is 2 to the 3. So each entry is 8 bytes. So it's like we had here. So same way, just like arrays. So what we're doing, hey, if I told you that I have an array of 512 ints, how big is that array? Yeah, each int is 4 bytes, right? Each int is 4 bytes, and if I have 512 of them, then that's 2,048 bytes, right? Because each int is 4 bytes. And then if I went to compute like an offset, so like what byte does the integer at index 2 start at? Well, index 0 starts at byte 0. Computers like in 0 indexing. Then the int at index 1 starts at byte 4, right? It's the next 4 bytes. And then index 2, well, that would start at byte 8. So an offset is just how many bytes from the beginning is something. So in this case, the offset of index 2 would be 8 because each integer is 4 bytes. So same thing for page tables. Yeah?
Could you go back to the single page table? Yeah, so the width of the page table is based on the architecture of the computer, like it's 64 bits, right?
So the width of the page table is based off like just how big a page table entry size is,
Okay.
which we saw before. Like it needs to store a PPN and then like at least a valid bit, and it should be a power of 2 number of bytes. So if you just...
Is the height arbitrary, or is it?
So the size of the PPN just has to be enough to store at least a PPN, or sorry, the size of the page table entry has to at least store a PPN and a valid bit. So based off that, that's how many bytes it consumes.
Like the height, like each 2 to the 9, is that arbitrary, or is that?
No, 2 to the 9 here is because we want each page table to fill up a page. So we just picked, just to make our life easier so that everything uses pages, we want the total size of that page table to be 2 to the 12, right? And then I would give you, each page table entry is 8 bytes, so we can figure out how many entries we need in order to fill up an entire page. Is that okay? Yeah, so same thing here. So just to verify that we are filling up a whole page, so 2 to the 9 is 512. So here, just think of the page table as just an array. So if I say you have 512 PTEs instead of int, and I asked you how many bytes that consumes, what's your answer? Well, it depends on the size of the page table entry, right? If it's 8, so if this is 8, it's just 512 times 8. And in this system, these are the numbers these equations should all be equal. So the size of the page table, AKA the size of an entry times how many entries there are, should be equal to the page size. And the size of the page table, it's just an array, so it's just the number of entries times the size of the page table entry. So just like an array, nothing's special. It's just an array. Yeah?
Is what's in the PTE for L2 and L1 the same as L0? Or I guess.
Sorry?
So what's in the PTE of L1 and L2?
Yeah, so there's a question, what's in the PTE for L1 and L2? The page table entries look exactly the same. So just have like a valid bit and then a PPN. But instead of that PPN representing, what this virtual page maps to, it tells me where I have to go to get to an L1 page table. So how that kind of looks is, let's take all of memory. Let's add a new page. So if we take all of memory, if we take all of memory and just divide it into some blocks, they're not all sized the same, but on your computer they will be. So these are all pages.
Excuse me.
Yeah.
Are you sharing your screen by any chance?
There we go. Sorry. All right. So these are your memory all divided up into pages. So how this works is, well, in order to start the translation, you have to have an L2 page table living somewhere. So there'd be an L2 page table, there would be a register that tells you where to start. So maybe it lives on, I don't know, whatever this is, physical page number 0. And then we can number them like 1. So this is, 2, 3, 4, whatever. This is how your memory looks like, your physical memory, and how it's divided. So your L2 page table, that would exist on a page. And then from the virtual address, right? We divide it up, so this is my L2 index, L1 index, L0 index, and then my offset, and then offset is 12 bits, and then the rest of them are all 9 bits. So, in order to do this translation, right, we're going to start off using this page table because, well, that would be set as a register. You need to know where to start, what page table to start with to translate an address. And then which entry we access depends on this index, right? So say it was index 0. You would look up the entry here, and let's say that page table entry tells us to go to ppn 1 or something. So if that index tells us to go to ppn 1, that means that's where the L1 page table is. So that means my L1 page table is here. And then which entry I access is determined by the index from the L1 index from the virtual address. Tells me which one of those 512 entries to access. Say, I don't know, it's another entry, and say it's telling us that the L0 page table is at physical page, I don't know, 4. Doesn't have to be all in a row. So now that means this one has my L0 table, and then say it has an entry there. I pick the entry based off the L0 index, and then that will tell me, hey, what physical page number is this virtual page actually supposed to represent. So say it gives me, I don't know, 2 or something like that. So that means this is the physical page for this VPN, where the VPN is like the same as before, it's these 27 bits. So in order to translate that single address, I just needed 3 pages worth of page tables. I needed one L1, or one L2, one L1, and one L0. All right, any questions about that? Yeah.
I was wondering, you said that the 3 pages, right, they store the same memory. So if you're...
I didn't say they store the same memory.
What's the difference between L2, L1, and L0?
So the difference between them is just what their entries represent. So L2, those entries all point me to an L1, and then L1 all point me to an L0. Then L0 has my translation for this VPN. But they all live in physical memory. They all need to live somewhere, right? Yeah.
One more question.
Yeah.
How is this saving space? We're using 3 times the number of page tables we need to, right?
So, yeah, the question is, how is this saving us space? So we're using 3 times as many page tables as we need to. So is that true? So before, when we had just one big page table, I needed a whole gigabyte now to translate a single address. But now I only need 3 pages, which is only 12 kilobytes, which is significantly less than 1 gigabyte, right? So I am saving memory here, because each level is small, and I just split it off into 3. But I don't lose any power, so we can demonstrate that too. So every process will just have one L2 page table. So how many different L1 page tables could it point to? Two to the 9, right, which is 512. So this could point to up to 2 to the 9 or 512. Actually, probably 2 to the 9 is better to write. And then each of those, each of those L1 page tables, every single one of them, how many different L0 page tables could it point to? 2 to the 9 again, right? So 2 to the 9, and we have 2 to the 9 of them. So in total, it could point to up to 2 to the 18 of these, right? And then for each L0 page table, each of those could point to 2 to the 9 as well, right? So they could point to up to, oops. So they could point to up to 512 different things. So in total, I could have an entry for up to 2 to the 27 different things, which is the same as before, right? So I don't lose any generality here. I'm just saving space in the case that my program doesn't need to translate all 512 gigabytes. If it just uses a little bit of memory, then it only has to use 3 small page tables. So it only has to use 3 pages. Yeah?
So, as we learned before, right, all of them were in the same block. Now we have divided it into 3 small chunks, right?
Yeah.
As both of them, all of them add up to 2 to the power 27, which was the original space, right? So what is the benefit of having small chunks? So do they get called specifically when there is a certain memory that's being used on that table?
Yeah, so we can see from this, in the worst case where I need to translate every single address, right? So say I needed to translate all 512 gigabytes, this will actually use more space because I'll use a gigabyte just for all my L0 page tables, right? So I have what? And we can verify that. So I have 2 to the 18 of them, and then each of them are the size of a page, so 2 to the 12. So that means that's 2 to the 30 right there. Makes sense. If I need to keep track of that many different translations, there's no way around it. But I'm also wasting some space because, you know, I have 2 to the 9 of these, and then I just have 1 of these. So I'm wasting, let's see, 2 to the 12. So this is 2 to the 21. So I have 1 gigabyte full of L0 page tables. I have 2 megabytes of L1 page tables, and I have 4 kilobytes of an L2 page table. So worst case, I'm actually wasting some more space, right? But the point is, your program doesn't need to translate every single address. So if I don't need to translate it, I don't have to have a page table to deal with that translation. So if I only need to translate 1 address, I just need 1 L2, 1 L1, 1 L0, and the rest of them just won't exist. If it tries to translate that address, it wouldn't be able to look up that table. It would get an invalid entry and just page fault immediately. So this is like, if my program doesn't need all translations, it's going to use significantly less space. Most extreme is if it only needs to translate, if it only uses 4 kilobytes and it needs 1 translation. I need 3 pages instead of 1 gigabyte page. So does that make sense? So I don't lose any additional power this way. I might, in the worst case, waste some more space, but from a single large table, but I'm only wasting an additional 2 megabytes and 4 kilobytes, which isn't much. Any other big drawbacks for doing this? So does that seem complicated? So in order to do a single memory access, how many memory accesses do I have to do to actually do the original memory access I wanted? 4, right? So before, like if I just had physical memory, I just had the original memory access, I just load it, whatever it is. Now, if I do this, I have to have a memory access to look up the entry in the L2 page table. Then I have to read that, figure out where I have to go, where I have to find the L1 page table, access the entry there. That's another memory access. Then that tells me where the L0 page table is. Then using the index, I find which entry I have to look up. That is my third memory access. And then it finally tells me the physical page number that this virtual page number refers to, and that's my fourth memory access. So I have made my computer 4 times slower if I'm using memory. Neat, huh? So remember, one of our goals was we wanted things to be as quick as possible. And this does not look quick at all, but we will solve this problem in the next lecture. But that's just to say that this will cause a lot more memory accesses. So again, any other questions or anything like that before we try and dive into an example? All right, so let us, and why we do this too, your memory allocator, the memory allocator in the kernel is really, really, really simple. It just uses a linked list called a free list. So given physical pages, all of your operating system, just when your computer boots up, just divides all of your memory into pages and maintains a linked list. So they call it a free list. And the unused pages themselves, since they're not being used for memory for your program, the page can have a next pointer to the next free page, and that would all be initialized whenever your computer boots up. And then after that, to allocate or deallocate memory, you do it at pages at a time. So it's real simple. If you want to allocate a page, you remove it from the free list, so now it's going to be used by your program. And to deallocate your page, you just add it back to the free list of pages. So just a simple linked list. Since one block is as good as any other block, the memory allocator is really, really, really simple. So, and again, this was our insight. We use a page for each smaller page table here, and then again, everything fits on a page. I only have to deal with pages. Whether or not that page is actually used for a page table or used for memory for my program. And again, how it works, I can have any number of levels of page table. They all work the same way. The page table entry in LN points to the entry for LN-0 or LN-1 until eventually you follow however many levels of page tables you have until you hit L0, and that has the physical page number for this virtual page number and has the actual translation. So let's do a question of how we would actually translate an address with just one level. So we are going to make a much smaller virtual address. So we're going to use the virtual address, and how it's going to be split off is we're only going to have 2 levels of page tables, still the same scheme where each level fits on a page. So we would only have a 30-bit virtual address this time, where 12 bits are used for an offset because our page size is still the same. It's to the 12. And then we have our L0 index, and then our L1 index. And these are both 9 bits. So in total, my address is going to be only 30 bits. So say I had the virtual address in hex 3 F F F F 008. And then I could tell you that, hey, somewhere in memory, there's a physical page with, I don't know, say it's 08, and I tell you that, hey, this page 08 is the L2 page table. And maybe I also tell you some information about it. Maybe I tell you at index 511 that actually, let's change the numbers. So say this one's living, on physical page 7, and then at entry 511, I say that its entry is physical page 8. And then I'll draw the page table here, or sorry, that's not an L2 page table, sorry, L1. L1 page table, sorry, only 2 levels. So somewhere in memory, we have physical page 8. It has an entry on it at index 512 again, where the physical page number is something like, I don't know. So this is how memory looks like. So we're going to try and translate this virtual address 3FFFFFF008. So in order to get my physical address, what's the easiest part to translate first? Yeah, the offset. So if it is 12 bits offset, that's the same as 3 hex characters. So mercifully, I don't have to do anything with it, right? So what are the last 3 hex characters of this physical address? Yeah. So the last 3 hex characters are, yeah, just 008 or 0x008, however you want to say it. So thankfully, we don't have to translate that. So how do we go about the rest of this translation? Yeah. Yeah, so now we have to take this whole address, turn it into binary, and then take it in groups of 9 at a time. So F, that is 3 ones, so 1, 1, 1, 1. Next F is 1, 1, 1, 1. This F is 1, 1, 1, 1. This F is 1, 1, 1, 1. This 3, that's just 2 ones, which looks like that. So kind of ran out of room a little bit, and then we group it by 9s. So here is what I would use for the L0 index, just like explained here. And then the next group of 9s, or 9 is all 1s. That would be my L1 index, right? Hopefully I drew enough 1s. It should all be 1s. So in order to do this translation, what would be given to you is what L1 page table to start. So it would be stated in the question or given to you that the highest level page table, in this case L1, is on physical page 7. So if we look at physical page 7, this is our page table we're accessing. We have to use the L1 index. So 9 ones, that is mercifully equal to 511. So because we're looking at L1 first, what does the page table entry tell us? Yeah, where the L0 page table is. So knowing that, so accessing this tells us we have to use the page table on page 8 as our L0 page table. So we would go ahead and use that. So now we're looking at this once we're using the L0 index. The L0 index is all 1, so that is also 511. So if we look into it, the entry at 511 is the physical page CAFE. So what is my resulting physical address for this virtual address we started with at the top? So same rule as before, right? So we're at our L0 page table. We get a physical page number from that. That tells us what the physical page number for this physical address is, right? So we already translated the offset, and now since we accessed L0, we finally got it, and it was CFA. So my total physical address is CAFE. FE008. Everyone okay-ish with that? Had to jump through some hoops, but we got there eventually. All right, what about if you were the operating system and you have screwed up? So, the L1 page table is at physical page 7, and we would get told to start there as our L1. But what about if they accidentally screwed up and the entry at 511 actually went to physical page 7? What would happen? What would our final translation be if this was the case? Segmentation fault. Nope. Yeah.
Is it 7008?
Yeah. The final translation would be 7708. Why is that? Well, it would just go level by level. So it would start off at the L1 page table. Then from the virtual address, it will say which index to use. So it would use whatever is at index 511. And if it was physical page 7, which happened to be itself, then it would say, okay, I'm going to use the same page table as the L0 page table now. So then it would use it as the L0 page table, look at the index from the L0 part of the virtual address, which happens to be the exact same thing. So it's physical page 7. So that would be the physical page for the virtual address. So we would just get 7008. So if it did this, this would probably cause a lot of headaches, and if your operating system did this, that means now your program can modify its own page tables. And that's probably bad because the kernel should be the thing that's managing that. So if your kernel really screws up and does something like that, if you knew what you were doing, you could map whatever, if you could control your own page tables, you could map your own pages to whatever you want and read other programs' memory and all of that fun stuff. So just to say that it's definitely the kernel that is the thing managing this, and it better do it right. All right, any other questions about that before we have a little simulator here? All right, so you have something to play with, and also this looks an awful lot like Lab 3. So just to show you, this simulates what happens in the MMU and actually uses the page tables you set up. So in this program, I wrote a bunch of helper functions. They look exactly like the ones in Lab 3. Basically, you are allowed to ask for a physical page. So allocate page table, that will basically just give you a page of memory. And then in order to actually translate an address, so this simulates actually translating virtual addresses, we need to go ahead and set a root page table, which in this case just looks like a global variable. So we create an L2 page table, it's a page, and we set our root page table to point to that L2 page table so that if we start translating a virtual address, it will use that for our L2 page table and then use all the indexes from the virtual address. So in order to successfully translate an address, I need at least an L1 page table and an L0 page table. So here I create a new L1 page table, and then here, this is how I link to it. So at index 0 in the L2 page table, I make it point to the L1 page table I just created. So this function PTE from page table, that will just create a page table entry that points to this page table. Basically, it will extract the physical page number and then set a valid bit. You can read that if you want, but it should just create a page table entry that points to that page. Then I need to create a L1 or an L0 page table, grab a new page, and then in the L1 page table at index 5, which we'll figure out why shortly, it will point to that new L0 page table. And then in that L0 page table, that finally has the final translation. So I have this function PTE from PPN, so it will just create a new page table entry with this argument as the physical page number. So if I call MMU, that will do the translation steps. So it will extract out what I should use for the L2 index, and then use this root page table to look up the page table entry there. That will tell me which L1 page table to use. I'll get the L1 index from this virtual address, get an entry there. It will tell me what L0 page table to use. I'll get the L0 index from this virtual address. Then it will tell me what entry to use for the what entry to get in the L0 page table, and that will finally give me my final translation. So if I go ahead and I run this program now, what is this, 12? So if I run this program now, I have it that if it cannot do a translation, it will just report page fault, aka there's no I can't follow entries to actually get a final translation. So if I do this, I'll see that the virtual address ABC, oh, it's not C. That's fine, yeah. ABDD EF translates to CAFE, oh geez, too many letters, DEF. And then the other one is just a straight up page fault. So why is that? Well, we should be able to figure out why I picked these indexes, because obviously this one actually made a valid address and this one gave us a page fault. So if I took the address, what address did we use? So if I took the address A, B, D, D, E, F, and I wanted to figure out which L2 index I'm using, which L1 index I'm using, what L0 index I'm using, how do I have to divide this thing up?
You convert it back to binary.
Yeah, I'll have to do that whole binary thing again, right? Because remember my virtual address, it'll be like 9 bits L2 index, whoops. Nine bits L1 index, 9 bits L0 index, and then 12 bits for the offset. So that means I don't have to translate this part, and if I write out the rest of it in binary, A is 1010, A is a 10. In binary, that's 2 10s, 10, 10. Then B is just 1, 1, 1, 0, 1, 1, and then D is what? 1, 0, 1, 1. So if I do that and then group it in 9s, that means this is my L0 index, right? Then this is my L1 index. And then the rest, of course, it's like a normal decimal number where it has leading zeros, so these would all be zeros. So if I look at it, my L2 index is just 0. What's my L1 index? Five, right? What's my L0 index? A lot of numbers, but we can cheat a little bit because the translation worked. They must all equal 189. Otherwise, this translation wouldn't have worked. So that's why it worked. It used all those indexes. I had an entry at each of those indexes so it could follow it to finally get CFA, like cafe, and then it replaced all of it except for DEF with cafe. So I got cafe DEF, and we're out of time. But you can play with this, you have this code. So just remember, bone for you.